Hi, in today's video we'll be looking at the concept of subspaces. First I'll be defining what a subspace of a vector space is, and then I'll give a way to quickly determine whether a given subset of a vector space is a subspace. In general, whenever we define a new mathematical object, we should ask what the sub-objects of that object are. For example, the sub-objects of sets are subsets. Most of the time, our objects will be sets of some sort with additional structure. In the case of vector spaces, this additional structure is the scalar multiplication and the addition that we've defined on our set. In such a case, we don't want the sub-object simply to be a subset of our set, but we also want it to retain some of the additional structure that we've defined. The most straightforward way to realize this is usually to require the sub-object to be a subset and to be an object of the type we're interested in. And this is precisely how we're going to define a subspace of a given vector space. Let V be a vector space over a field F. A subset U of V is called a subspace of V, if it is also a vector space with respect to the same addition and scalar multiplication defined on V. To paraphrase, we require two things for U to be a subspace, namely that it be a subset of V and that it also be a vector space. It's also important that U have the same addition and scalar multiplication as V does. So if we've defined an addition plus V and a scalar multiplication times V on V, then we also want U to be a vector space with respect to these operations. Now, let's unpack the definition we've just made. So you don't forget it, I've given a brief summary of the definition up here. Since we want U not only to be a subset, but also a vector space, I figured it would be a good chance to review the definition of a vector space, so we know what we're actually demanding of U. Recall that a vector space V over a field F is a set V, together with an addition, which is a function from V cross V to V, and a scalar multiplication, which is a function from F cross V to V. Moreover, we require the addition to satisfy four properties. So first we want it to be commutative, then we want it to be associative, and we also require the existence of some special objects, namely we want there to exist an additive identity and additive inverses for each element in V. We're a bit less demanding of the scalar multiplication, which we simply want to be associative, and we also want the unit element in our field to be a unit with respect to the scalar multiplication. Finally, we'd like the two operations we've defined to be compatible with each other, which means that we require two distributive properties. Let's consider what this translates to for a subset U of V, which is supposed to have the same addition and scalar multiplication as V. In order to have a vector space, we need a set together with two operations. But we're already given the set U, which is a subset of V, and we're also already given the operations because they have to be the same ones as on V. Looking at the 8 properties that we need to satisfy, there are two that stand out, and these are the existence properties down here. These mean that in order for U to be a vector space, U needs to have an additive identity. Let's call that 0U. And also additive inverses for each element U and U, so we need minus U for each U and U. It will turn out, because U is a subset of V, that the additive identity of U has to be the same as the additive identity of V. And also, the additive inverses defined on U are the same as taking the inverses in the larger space V. As you can imagine, it would be pretty tedious if we had to check all of these 8 properties each time we wanted to determine whether a subset is a subspace. In fact, we can reduce the number of things we need to check down to 3, and in order to see this, we need to think about what can go wrong. The most obvious things that could go wrong is that U could fail to have an additive identity, or fail to have additive inverses for each element in U. Then there is a more subtle issue concerning the two operations. To illustrate this, consider the subset 0, 1, 2 of R. If we want this subset to be a subspace, we need to inherit the addition and scalar multiplications from R. But now if we want to, for example, add two elements that are in the subset, so 1 plus 2, we notice that the third element actually doesn't live in this subset. So 1 plus 2 should be 3, but 3 isn't an element of the subset. What we require would be that the addition would be a function from U cross U to U. However, in this case, we don't have such a function because, for example, 1 plus 2 gives an element which does not live in U. So it's not actually a function from U cross U to U. Instead, it would be a function from U cross U to V, which is not what we want. This example shows that the addition and scalar multiplication on V can fail to restrict to functions on U. Another way of saying this is to say that U could fail to be closed under addition or scalar multiplication. Abstractly, this failure of closure would be to have elements U and V in U, but not have U plus V in U. So this is the situation we want to avoid. There are 5 properties remaining, but it will turn out that these properties are automatically fulfilled once we make sure that the addition and scalar multiplication on U are well defined. This is simply because these properties hold on the larger space V, and each element in U is also an element of V. Let's summarize the previous discussion in the following proposition. A subset U of a vector space V is a subspace of V if and only if U satisfies the following 3 conditions. First, we want the additive identity 0 to be an element of U. Second, we want U to be closed under addition. This means that if U and V are elements of U, then so is U plus V. And finally, we want U to be closed under scalar multiplication. This means that if A is an element of F and U is an element of U, then A times U is an element of U. So in short, a subset U of a vector space V is a subspace of V if and only if it contains the additive identity, is closed under addition, and is closed under scalar multiplication. We need to prove 2 directions. First, suppose that U is a subspace of V. We need to check that properties A through C hold. Let's start with property B. We know that because U is a vector space in its own right, that the function plus from U cross U to U is well defined. In particular, this means that an element U comma V of U cross V is mapped to the element U plus V in U. Or in other words, if we have elements U and V in U, this implies that U plus V is in U because the operation plus that is defined on U is a function. Virtually the same argument applies to C for the scalar multiplication. We know that the operation of the scalar multiplication on U is a well-defined function. And this implies that if we have an element A in F and an element U in U, then A times U has to be an element of U. So we verified that B and C hold. Now let's turn to property A. We need to check that U contains the additive identity of V. However, so far we only know, because U is a vector space, that U contains its own additive identity. Let's call it 0U. To show A, therefore, we need to show that 0U is equal to 0V. From a previous proposition, we know that if we multiply any element in V by 0V, we get back 0V. Since 0U is just such an element, we have that 0V times 0U is equal to 0V. But now, because we've already seen that U is closed under scalar multiplication, this shows in particular that 0V is an element of U. Another thing we know about 0V is that it is the additive identity of V. This means that V plus 0V is equal to V for all V in V. However, because U is a subset of V, this also holds for all U in U. So we can replace the condition for all V in V by U in U. Hence, 0V is also an additive identity of U. But now we have the situation that 0U and 0V are both additive identities of U. But we also know that additive identities of a vector space are always unique, and so it follows that 0U is actually equal to 0V. And this shows condition A. We've shown one direction and now move to the only if part. Let's suppose that U is a subset of V that satisfies conditions A through C. To show that U is a subspace of V, we need to make sure that U is a vector space. Condition A assures that U has an additive identity. This is the same argument we've seen before. Because 0V is an additive identity of V, we have that 0V plus V is equal to V for all V in V. Now let's take some element U in U. Because U is a subset of V, this implies that U is also an element of V. Hence, the above equation holds, and we have that 0V plus U is equal to U. But now, the element U we chose in U was arbitrary, so we conclude that this equation down here holds for all U in U. And this is just the definition of an additive identity in U. Thus, the previous argument shows that U has an additive identity. Now, conditions B and C assure that the addition and scalar multiplication defined on U make sense, so that they are well-defined functions. There's one final existence property that we need to check, namely the existence of additive inverses. So let U be an element of U, and we now need to check that U has an additive inverse in U. From lecture 4, we know that -1 times U is equal to the additive inverse minus U. And this equation holds in the vector space V. However, because U is closed under scalar multiplication, and -1 is an element of the field, and U is assumed to be in U, this means that minus U is also an element of U. So now we just need to check that this minus U is indeed the additive inverse of U in the vector space U. To see this, we simply add minus U to our element U, and we know that this is equal to 0V in the vector space V. However, we've seen previously that the additive identity of V is also the additive identity in U. So minus U is indeed an additive inverse of U also in U. Because the U we chose was arbitrary, this holds for all elements U of U, so each element U of U has an additive inverse that also lives in U. So we've confirmed that U has additive inverses. Now the remaining thing that we need to check are the identities that need to hold in U. However, it turns out that they automatically hold in U because they hold in V, and U is a subset of V. To illustrate this, let's look at the commutative property. So we need to show that U plus V is equal to V plus U for all U and V in U. So we let U and V be elements of U. But because U is a subset of V, this implies that U and V are also elements of V. But V is a vector space, so U plus V is equal to V plus U in V, and hence also in U. But the elements U and V we chose in U were arbitrary, so in fact, this equation, U plus V equals V plus U, holds for all U and V in U. The exact same line of reasoning holds for all the other equational properties, so we just take whatever elements we need in U, then we say, okay, because U is a subset of V, those elements are also in V, hence whatever equation we're trying to show holds in V, and this means that it also holds in U because U inherits the addition and scalar multiplication from V, and thus whatever property we wanted to show holds for all elements in U. To conclude, let's check that we remembered to get everything. So in order for U to be a vector space, we need a set, which we already have, U, and we need two operations. And we saw that B and C make sure that the operations of addition and scalar multiplication make sense on U. Then we also need U to possess an additive identity, which we saw follows from A, and we also need U to have additive inverses, which we saw follows from A and from the closure of U under scalar multiplication. Finally, all of the other identities that elements of U need to satisfy follow from the fact that U is a subset of V, as we illustrated in the case of the commutative property. So indeed, we've checked everything, so U is a vector space, and this means that by definition, U is a subspace of V. Before wrapping up, I'd like to remark how useful this proposition is, and we'll be using it all the time to check if subsets are subspaces. So instead of checking 10 things, we just need to check 3. As an additional comment, instead of requiring an A that the additive identity be an element of U, we could also require equivalently U to be non-empty. To see that these two conditions are indeed equivalent, we note that the one direction is clear, since if 0V is an element of U, then obviously U is not empty. On the other hand, if U is non-empty, then there exists some element U in U, and if we now multiply this element U by 0, we get 0, and because by C, U is closed under scalar multiplication, 0 also has to be in U. This shows that if U is non-empty, then it has to contain the additive identity. I mentioned this alternative proposition only so you don't get confused if you see it somewhere, or if someone uses it in a proof to show that a subset is a subspace. Generally, with these types of propositions where one has to check less things than one otherwise would have to, it's usually a good idea to understand why they're true and not just memorize the 3 things you have to check. Let's summarize what we've seen in this video. We defined a subspace U of a vector space V to be a subset of V that is also a vector space with respect to the same operations. Next, we saw that we don't need to check all of the properties of a vector space. It's sufficient to check just 3. So we have to check that the additive identity is an element of U, that U is closed under addition, and that U is closed under scalar multiplication. And in this case, a subset U of V is automatically a subspace. This subspace concept is really important and will come up all the time, and so we'll be getting a lot of practice with it next time when we look at examples of subspaces. I hope to see you then.